Greetings, I bid to Dr. Nurul Akmar and welcome to Group 7's Smart Sampling Chamber Group Presentation. For our problem statement, we divide it into three aspects. Number one, our vision, which is we want our design to be ergonomic as to protect both the patients and healthcare givers from back pains and neck strains, promote privacy and hygiene during sampling process, and most importantly, portable and affordable for mass produce. Number two, issue statement, which is, as of right now, there are few sampling chambers being used in Malaysia due to the high cost and low rate of patients being swab tested at a time. Should this issue prevail, we are concerned on the safety of both the patients and healthcare givers during the sampling process through the common mediums such as walk-in tents. And number three, our method, which we are utilizing Google Forms as a means to obtain public and professionals' opinion on the best design. For our objectives, we want to design a sampling chamber that meets specific design requirements. We also want to develop a virtual prototype according to design specification and perform product validation study and design refinement if necessary. For product design specification, we have listed 5 important features for our sampling chamber. They are: the sampling chamber should possess good aesthetics for promotional value. Next, it also should be easily detachable for ease of storage. And the sampling chamber should also be reusable, portable, and ergonomic. For concept generation, we have come up with 5 concept designs. The first design has a triangular shape as a whole, possesses acrylic perspex as the walls material, a door entrance type, roller sleeves mechanism, normal air vents, dovetail slots for installation method, and clear acrylic for window material. The second design has a rectangular shape as a whole, Oxford polyester as the walls material, roll-up door and zip as entrance type, vinyl protective sleeves, mesh flynet ventilation, and stainless steel nozzles and tubes for sanitization method. The third design is hemisphere-shaped, nylon cloth as a walls material, normal zip as entrance type, and vinyl sheet as a windows material. The fourth design utilized pressure-molded plastic sheets for the wall material, a normal door for entrance type, wraparound rubber gloves for sleeves mechanism, double vents ventilation, have nuts, bolts, and rivets for fasteners, and clear acrylic for window material. The fifth and final design is intended to use Oxford polyester for walls material, roll-up door and Velcro entrance type, also wraparound rubber gloves as sleeves mechanism, normal vents, and a clear acrylic as window material. Proceeding to the concept evaluation, we used a puck chart emphasizing on 4 criterions, which are shape or weight, features, installation, and production. As you can see, here concept 2 ranked first, followed by concept 1, concept 5, concept 4, and concept 3. Next, we further evaluated our designs using the weighted scale, focusing on 6 selection criteria, which are ergonomic, aesthetics, sanitization, ventilation, portability, and affordability. We have determined, yet again, concept 2 to rank first, followed by concept 3 and concept 5 at third rank. As a result, we have decided to continue developing concept 2, and here is our final design.
After selecting our design from the morphological chart, we have decided to expand a bit more into it. One of the changes which can be noticeable is the roof design, which was changed from a pointy top to a flat top to reduce potential wind resistance. Another could be said for the built-in table, which we decided to make it detachable and having adjustable heights instead. The feet was also changed from 4 feet to 6 feet for better stability. Nozzles were added in the corner for more detail and ease of installations regarding the tube to flow the sanitization fumes. But overall, we considered the cost to manufacture this product, which can be said to cost roughly around 6,000 to 8,000 overseas. Installation will only take a couple of minutes and will need 2 manpowers minimum. That said, these frame pillars are telescopic to 3 adjustable heights so that it is portable. The flow of installation is by setting the frame, attaching the table, sliding the divider through the bottom, and finally sliding the cloth wall from the top. The full size of this chamber while it is unfolded is around 2.1 meters tall, 2.07 meters long, and has a width of 1.07 meters. It can only fit one patient and one frontliner.
The material selection consists of few parts, that is, main frame, wall and roof, door, ventilation, sample window, gloves, sample table, and the auto sanitization system. There are few factors to consider in choosing the main frame. For example, it must be easy to assemble and disassemble, easy to manufacture, or available in the market to save some cost, a simple design, strong and durable. And for that, we choose the stainless steel as the material. We have done a comparison to select the best material for the wall and roof. Like the table shown, it's between acrylic, Oxford polyester, and nylon. So we decided to use 210D Oxford polyester for this project because it consists of 100% polyester, high strength, good elasticity, and easy to wash and dry. As for the door, the material is the same as wall and roof, which is the Oxford polyester. It was secured with the zipper mechanism, and it could be a roll-up door, so it is safe to avoid contact. Next, we will use mesh wire as the ventilation for this project because it easily fit with the Oxford polyester material. Material for sample window is the transparent vinyl curtain, and there will be a vinyl protective sleeve attached to the sample window. So the frontliners will only use reusable gloves, and it can be changed after another patient. Moving on to the sample table, we will use a high-density polyethylene plastic for the tabletop and gray powder-coated steel tubes as the frame. So from a foldable table, we have modified to our own design. Lastly, the auto sanitization system. This system consists of polyethylene microtubing, stainless steel nozzle that are fitted to sprinkle the mist of disinfectant, auto switch off when the sensor detects no one, and then here is the pump box, which um, consists of switch cabinet with light barrier and time relay, water filter, high pressure pump, disinfectant canister, and automatic dosage pump.
Our part analysis was done directly using SolidWorks Express simulation. We considered the bolt, nuts, and rivets to be an important part in the product as it holds more components into place such as the arms and the pillars. A load of 225 Newton was applied as it was an average push force by a man. We detected that critical point forms around the necking nearing the head of each bolts and rivets. In order to avoid this problem, we give the product better longevity by adding fillets, which would decrease the critical points at a specific area nearing the head of the components. Next, we will analyze the pillow of the chamber, which is crucial as it holds the product to be stable. We found out that the thickness is the right amount, which was around 2.5 millimeters. Any more would be pointless, and any less would decrease manufacturing costs, but also at the expense of durability.
Hello, my name is SMJP2112-02. For my part, I'm going to talk about an engineering analysis, manual calculation. The type of frame and structure we use is a square hollow section with the type of ASTM A500 mild steel and the size of the 50 times 50 times 1.6 millimeter. Next is the type of the connectors used. which is bolt and nut. M12 M12G12 galvanized iron with the ISO AB screw head 4017-4016. Okay, next, for the allowable stress calculation part, you need to find the cage weight of the cage frame, which is 40 kg. And then we find out that the total area of the booth is 3048 mm times 1524 mm. And then the entrance height is 2006.6 mm with the maximum height of 3124.2 mm. And then by looking at the solid work, we get the yield strength grade B equals to 290 megapascal, and we get the factor safety of equals to 3. So this gives us for the allowable formula. Using the allowable formula, we get yield strength over safety factor equals to stress allowable. We get the 290 times 10 to the power of 6 over 3, and then we get the answer is 96.667 megapascal. Therefore, the allowable stress is 96.667 megapascal. The next slide is we talk about assuming another tube with different dimension. if the another tube with different dimension, we must find the average shear stress AM equals to 0.035 meter times 0.057 meter equals to 0.00200 meter square. For the at point A is T equals to 5 millimeter. We got the tau A equals to T over 2 T AM equals to 35 Newton meter over 2 times 0.005 meter times 0.057 meter square. And you get 1.75 megapascal. For the point B equals to T equals to 3 millimeter, tau B equals to T over 2 T AM equals to 35 Newton meter over 2 times 0.003 meter times 0.00200 meter square. And then we get the answer 2.292 megapascal. And then the benefits to the society that after we done this project. During this pandemic, COVID-19, this project has been a great exposure to the students to grasp this real situation that our relentless health worker has faced each day carrying out sampling tests on their patients. Second, the threat given by the COVID-19 pandemic makes us to explore more deeper into the current project. Then, due to the COVID-19 pandemic, we also did implement our engineering towards designing efficient, safety, and portable sampling chamber. And with that, that's all from us regarding about this project. Thank you, Doctor, for listening, and have a nice day.